Hi everyone, good afternoon. This is Bilal. Welcome to tutorial 7 entitled the Query Optimization Part 1, the logical plan, which is intended for both majors, MET and business informatics. Okay, I hope that all of you are fine and everything is healthy and good at your site. Before diving deeply into our tutorial, make sure to bring your essential tools to solve the problems listed and covered by this tutorial. So here's the stuff we are gonna need during this tutorial: the tutorial notes, tutorial slides, practice assignment number 7, and our true good friend, the CMS, in case we need anything else from the course material. Okay, so yeah, we need a calculator. Yeah, it takes time to load, takes some time. Okay, and we need a sketchpad. Yes, decrease the size of the brush. Okay, fine. Now we are ready to take tutorial 7. Okay, so let's review what you have been taught during this course until now. Okay, so during the first 6 lectures and tutorials, you have been taught about the following topics: the different types of indices, such as primary index, secondary index, multi-level index, sparse index, dense index. Then during tutorial 2, we've learned about the B+3 data structure used to build an index to make the search process faster in most of the database management systems available today. Okay, then we have learned about the K3 partitioned hashing, bitmap index, and linear hashing, extendable hashing. Okay, and these were intended for relational databases. We have learned about 2 special data structures for spatial databases, which are R trees or region trees, okay, and quad trees. So up till this moment, we were outside the database management system architecture. Okay, we were creating indices from outside the database management system or the database engine using the SQL command, such as, for instance, create an index on column age from table students, and so on. Okay, so starting from today, starting from lecture 7, we will dive deep into the database management system architecture. We will learn in a very detailed way about its main components, which are these components, such as the query processor, the transaction manager, the log manager, the recovery manager, the buffer manager. Okay, so we will spend the next 3 tutorials learning about the query processor. Okay, so we have tutorial 7, query processor part 1, the logical plan, and tutorial 8, query processor part 2, physical plan, and tutorial 9, query processor part 3, physical plan. Okay, okay, so let's bring the lecture slides from the CMS. Okay, search for lecture 7. Yes, lecture slides. Download, open. Okay, so let's refresh your memory about what you have been taught during the lecture 7, and let's revise some of the concepts covered during the lecture before starting proceeding and solve some problems. Okay, so we are gonna focus today on the query processor, and the query processor is responsible for processing the input SQL statement or SQL query by doing the following 4 steps. The first step is to parse the SQL query and convert it to a parse tree, which contains all of the necessary details to plan for how to efficiently execute this query, such as the table we are selecting from, the attributes we are using, and so on, and the conditions. Okay, so the first step is to parse the query. Then the query processor try to compute the best logical plan and the best physical plan for the given SQL query. Okay, so the logical plan, okay, considers the order of operations in the given SQL query. In other words, is it efficient? Is it more efficient to compute the select before the join, or the join before the select, or we need to perform the projection before all of the other operations to make the SQL query take the less time possible, okay, to execute. And the physical plan, okay, considers the actions, the real actions, okay, on the bare metal or on a very low level of hardware and software, okay, the actions of that need to be taken to execute the SQL query, such that reserving a swap area and the random access memory, loading pages or a set of buckets from the hard disk into the main memory, scan the full table, create an index, use an existing index, and so on. So the physical plan is about actions, okay, and the logical plan is about the order of operations to be executed, the correct order, or the most optimal order, okay. So today we will learn about the second step, the logical plan builder, how the SQL query processor chooses the most efficient logical plan, okay, for a given SQL statement. So here is an example. We have a query here: select distinct B from R join S, where R.A equal 10. Okay, we have more than 3 different ways to execute the same SQL query. Okay, all of them will give us the same results. However, one of them will run faster than the other 2. Why? Because the order of operations matters and affect or has a strong impact on the runtime or the number of tuples processed during the SQL statement. Okay, so for example, if we performed the select before the other two operations, the distinct and the join, okay, we will reduce the number of tuples that propagates upward till the final step in the given SQL query, okay, this query. So the main goal is to reduce the number of tuples that propagates from the first step till the final step in any given SQL query, okay, to reduce the runtime as much as possible. So this plan is better than these two, okay. So we reduce the number of tuples in R by performing the select, then the projection, then we join the resultant tuples from this branch with table S. And it's much better than joining all of the tuples in R and S, then performing the select, then performing the projection, okay. So we have two types of optimizers: the heuristic based and the cost based. The heuristic based applies some of good practice and rules, heuristic rules, okay, that may work for most of the cases and succeed to reduce the runtime of a given SQL query. And the cost based is based on probabilistic equation and mathematical formulas to predict the cost of each logical plan and then select the cheapest one. So these are the three main rules of the heuristic based: perform a selection early to reduce the number of tuples, perform a projection early to reduce the number of attributes, okay, to save memory and save time, perform most restrictive selection and join operations before other similar operations. So all of these three rules intend to reduce the number of tuples, reduce the number of attributes, okay, reduce the size of the data or the amount of data we are working on during our SQL query, okay. And you have already seen this example during the lecture. By pushing the selection down, we improve the performance of this SQL query. So let's skip this part and we are gonna focus, okay, in this tutorial on the cost-based query. We are gonna solve a lot of problems about the cost-based query optimization, okay. So the cost-based query optimization is about the following, or the main idea is to generate a good or enough amount of possible logical plans for any given SQL query and estimate the costs for each possible logical plan and pick the minimum or the cheapest plan. This is the main idea beyond the cost-based query optimization. So we have a set of statistics we need to know, because we are going to use them during all of the upcoming tutorials and all of the problems we are going to solve today. So we must be familiar with these notations or terminologies, okay. T of R represents the number of tuples in R. S of R represents the size of each tuple in table R, and B of R represents the number of blocks used to store relation R, okay. VRA, the number of distinct values in relation R for column or attribute A, okay. Nice and easy, clear, okay. So here we have a table here, and here's the statistics for this table. The number of tuples in table R are 5, okay. The number of distinct values in column A are 3, cat, dog, bat. And in column B we have one distinct value, which is 1. And in column C we have 5 distinct values, 10, 20, 30, 40, 50, and in column D we have 4 distinct values A, B, C, D. Okay, given the unit size for each column, by summing all of these or by adding all of these values together, we this gets us the total size in terms of bytes, okay, for each tuple inside table R or relation R. So now, after understanding the main idea beyond the cost optimization query optimizers, okay, now we need to know how to calculate the number of tuples for any given SQL query. So we have to estimate the cost. We are going to estimate the cost for different types of SQL statements, such as cross product, select condition equal, select less than, select not equal, how to do the join, how to perform the cost of the join, and how to compute the cost for SQL queries with multiple conditions or compound conditions, such as and or. Okay, and after that we are gonna practice these rules by solving the following practice assignment or the following sheet of problems. Okay, so my advice for you is to watch the lecture to understand the origin of each of these rules and the story beyond it, okay, to be able to solve any given problem and to compute the cost for any given SQL query. Complex one, simple one, one with compound condition, one with simple condition, and so on. So the first thing we are gonna look at is how to compute the cost for a cross product between two relations or two tables R1 and R2. So let's refresh your memory how to compute the cross product for given two tables. Okay, so we have table R1, this is R1, and we have table R2, this is R2. The size of any tuple inside table R1 is S of R1, and the size for any tuple in table R2 is S of R2. The number of tuples in table R1 is T of R1, okay, and the number of tuples in table R2 is T of R2. So how do we perform the cross product? Well, we create a third table R3, all the result sets, okay, the result of the cross product between R1 and R2 are gonna be stored inside R3. So we take each tuple from R1 and combine it with each tuple from R2. So each one of these tuples in the result set is composed of two parts. One of them comes from table R1 and the other one comes from table R2. So as I have said just a few moments ago, we take each tuple from R1 and combine it with all of the tuples in table R2, and we repeat this for all tuples in table R1. So the size of the result set, or the number of tuples, okay, resulted from this cross product is gonna equal T of R1 times T of R2. This is times, not a cross product, okay. So the cost of this logical plan for cross product is T of R1 times T of R2. Okay. and we express the cost in terms of the number of tuples that propagates. Okay, don't forget this. We express the costs in terms of the number of tuples resultant from executing this SQL query, or that propagates along the SQL query. Okay. Now the size of each tuple in the result set is gonna equal S of R1 plus S of R2. Okay. Next, select all of the tuples from relation R which have attribute A equal value small a. So what's the number of tuples? Okay, that result from executing the following SQL query given this condition. So think about it this way. This is table R, and we want to select all tuples with value A equal A small, or with column Z equal value. Okay, so what is the probability that this tuple will be the answer or will belong to the result set? Okay, the probability or the chance is 1 over all of the distinct values. Okay, so if we are considering column Z, we have here in our statistics the number of distinct values in this column. So 1 over VRA, okay, or 1 over, sorry, VRZ. So get me a new one, discard. The probability that a specific tuple belongs to the result set is 1 over VRZ. Okay, VRZ, the number of distinct values in table R for column Z. Okay, you can think about this way. If you are rolling a dice, what's the probability that you will get number 1? Well, 1 over 6, 1 over all of the possible values. So 1 over VRZ, and this is for a single tuple. So let's compute the probability for all of the tuples in table R. Multiply them by T of R. T of R over VRZ. Okay. And remember, this is a probability, so you may get numbers with fractions. One of you can say to me, hey, there is no 1.6 tuples. Okay, this is a probability function or probability theory, so it gets us estimation or prediction of the number of tuples, so non-exact values. Okay. Okay, you can replace any distinct value, any formula of distinct values, the number of distinct values, with the domain. Okay, the domain of a specific attribute. Okay. Okay, let's compute the number of tuples resultant from executing this query. Select all tuples from table R with attribute Z greater than or equal a given value. Okay, so let me visualize the concept. We wanna know the origin of this rule, T of R over 2. Okay, so suppose we are searching for, or we are selecting all tuples with Z greater than 10, greater than or equal. Okay, so suppose we have two cases. The first case is a table with all values greater than or equal 10. So in this case the number of tuples equals T of R. And the second case, all of the tuples are less than or equal 10, so this returns 0. Taking the average of two cases, T of R plus 0 over 2 gives us T of R over 2. Okay, and we have a second solution, T of R over 3, and a third solution. If the examiner gives you the following information in the question, you can use it. You can use this formula to compute the number of tuples. Okay, maximum minus value plus 1 over maximum minus minimum plus 1. This is for greater than or equal. Okay, select greater than or equal. Greater than or equal, greater than, less than or equal, less than. For greater than or equal, maximum minus value plus 1 over maximum minus minimum plus 1. For greater than, the same denominator and the same numerator, except we have to remove this plus 1. So maximum minus value. Let me check. Yeah, correct. Maximum minus value. Okay. For less than, value less than or equal minus minimum, minus minimum plus 1 over maximum minus minimum plus 1, the same range. Okay, the same denominator. For less than, only value minus minimum over the same denominator. Okay, so this is how we calculate the number of tuples for select greater than query. Select not equal. Okay, so we can assume that this will return most of the table, so we can overshoot and say this will return T of R. Okay, which means that most of the table are equal to value except 1 or 2 tuples. Okay, or the opposite. The opposite. Most of the tuples in the table are not equal to this value in the condition, given in the condition. Okay. Distinct. Okay, so suppose that, let's assume each tuple in table R is duplicated, so half of the table will be omitted by the distinct operator. Okay, so this will return T of R over 2. Okay, for complex conditions or compound conditions, let's consider this select statement. Select all of the tuples in table R which satisfy both subconditions, A equal value 1 and B less than value 2. Okay, so the tuples that satisfy the first condition are the same, must be the same that satisfy the second subcondition or condition 2. So let's calculate the number of tuples that satisfy this subcondition. We have T of R, the number of tuples in table R, equal 10,000, and the number of distinct values in table R for column or attribute A equal 50. Okay, and we have illustrated this tuple just a few moments ago, and its rule is T of R over VRA according to the probability. Okay, the probability theory. So T of R over VRA, 10,000 over 50 equals 200, for example. Okay, so the number of tuples from relation R that satisfy the first subcondition is 200. So we wanna know right now how many of these 200 satisfy condition 2. So we will apply the rule of this less than over the 200, not the whole T of R, not the whole 10,000, okay? Because out of the 10,000 we have 200 tuples that satisfy the first condition, subcondition, sorry. We want to know how many of them satisfy the second condition, okay? So 200 over or multiply by 1 over 3 or 1 over 2 equals 67. Okay, however, the case is different if the compound operator is OR, not AND. Here we have two separate subconditions. The number of tuples or the tuples that satisfy condition 1 are not necessarily the same tuples that satisfy also condition 2. So we compute the number of tuples for subcondition 1 and condition 2 separately. After that we add them together. So this one is gonna be T of R over VRA 10,000 over 50 equal to 100, and this is gonna equal T of R over 3, which gets us 3,333. So adding these two terms together, 3,533 tuples may satisfy both conditions, or one of them, or both of them, okay? Because this is compound operator. The join, okay. Now, how many tuples results from performing join between tables R1 and table R2? We want to join these two tables or these two relations. So here are the two rules, okay, to compute the number of tuples for the join, any join query, okay, to join two tables or two relations R1 and R2. So let's inspect the join operation to understand these two rules, okay? Discard. So we have table R1 and table R2, and we want to join both of them. So we must have a common column in both these two relations, that we join these two tables using this common column. So if we have a common column Y, so there must be common column or common values. So we want to search for these common values, okay, from table R1 into table R2 to find the matching tuples or the tuples with the same value for attribute Y, and join them and add them to the result set. This is the result set, okay? So we will iterate over all distinct values or over all values in column Y for relation R1, and for each value we will perform a select equal, or we will search for this value inside table R2. So the cost of select equal is T of R2 over V R2 Y, okay, and we are gonna do this for all tuples in table R1. So we will multiply this fraction by T of R1, and this is the first case where V R1 Y is less than V R2 Y. The number of distinct values in table R1 for column Y is less than its counterpart in table R2. so we will perform less select statement or less search operations. The other case, we will change the denominator where the number of distinct values in R2 is less than R1. So it will be again T of R1 over V R1Y times T of R2. And to generalize these two cases, we will solve using this general formula. T of R1 times T of R2 over the maximum of the number of distinct values in both table or relations R1 and R2 for column A or for attribute A. Okay, please remember this is the common column or the common attribute. Okay, we use during the join. And the size of each tuple in the result set equals the size of each tuple in R1 plus the size of R2 minus the size or the unit size of the common column, because it's common, so we have added twice. So let's remove one of them. Okay, we are finished. Okay, so now let's practice these rules by solving the following questions in practice assignment 7. You will find it on the CMS. Okay, try to solve the problems, okay, by yourself. So first, after watching the lecture, studying the material, doing our best, open the practice assignment, not the solution, and try to solve all of the questions contained by this practice assignment by yourself. Then look at the solution. So let's start with question number 1. So let's solve question number 1. Let relation R, which has the following 3 attributes or columns A, B, and C, be a relation where T of R, I will fix this, I'm sorry, T of R equal 10,000 and VRA equal 50. The number of distinct values in table R for attribute A equal 50. Estimate the size of T of S if S is each one of the following select statements. Okay, so let's start with the first one. Select all tuples with attribute A equal 10 and attribute A greater than 20 at the same time. This is AND operator, so the tuples that satisfy condition 1 must satisfy condition 2. And this is impossible, okay, because if they have attribute A, the value attribute A equal value 10, it's impossible that they satisfy the second subcondition 2. So this is a contradiction, okay. This gets us 0. T of S equals 0. The second one, A equal 10 and B less than 20. Okay, let's compute the number of tuples that satisfy the first subcondition, A equal 10. Select A equal 10. Okay, so minimize it, bring me the scratch pad and minimize it. Let's solve this problem here. Okay, so we have T of R equals 10,000 and VRA equals 50. Okay, so the first part, the number of tuples that satisfy the first part, yes, the rule is T of R over VRA. Okay, this is A. Okay, 10,000 over 50 gets us 200. Okay. Okay, now how many out of these 200 satisfy condition 2? So, over 2 or 3. Okay, so this is the first one. The second one, sorry, the third one, a equal 10, again 200, or, so plus, this is or operator, b less than 20, so t of r over 2 or 3, 10,000, okay, 10,000 over 3, 3, 3, 3, 3 plus 200 gets us 3,533. Here is the model answer, okay? It would be better if you read the problem twice or 3 times before rushing out and trying to solve the problem by yourself, okay? Read the question twice before solving the question. Question number 2. Consider the following 3 relations and their corresponding important statistics. Then compute the natural join R and S and U. So we could join R and S first and join the resultant tuples with U. So here are the statistics. So let's review the statistics of the 3 relations. Relation R has 2 attributes, A and B. The number of tuples in relation R is 1000, and the number of distinct values in relation R for attribute B equals 20. Relation S has columns or attributes B and C. The number of tuples in S is 2000. The number of distinct values for attribute B and C equals 50 and 100. Relation U has 2 attributes C and D. The number of tuples in relation U equals 5000, and the number of distinct values for attribute C equal 500. Okay, in order to join 2 relations, there must be a common column. So R and S. Let's first join R and S. R and S has common column B, and the rule says multiply T of R by T of S over the maximum of both distinct values in both relations R and S for the common column, okay, for the common attribute. The maximum between 20 and 50 is 50. Okay, so 1000 times 2000, 3 zeros, 3 zeros gives us 2 million over 50 gets us 40,000 tuples. Okay, we can consider these 40,000 tuples as a relation, okay, that we need to join it with relation U. Okay, so since we have just joined relation R and S, the resultant 40,000 tuples has columns A, B, and C. Okay, so we can join these 40,000 tuples with relation U based on column C as its common column. Okay, okay, so multiply the 40,000 by 5,000, okay, over the maximum of the number of distinct values for attribute C in relation U and the number of distinct values for attribute C in relation S. Okay, remember that when we join 2 relations, the resultant tuples contains the attributes of both relations. Okay, so the resultant tuples has relation C. These 40,000 has relation C, so we can join them with relation U based on column or attribute C. Okay, question 3. Question 3 is a really interesting question. he gives you the following statistics about these four relations: W, X, Y, and Z. Okay, so we have four tables: W, X, Y, and Z. W has two attributes A and B, X has two attributes B and C, Y has two attributes C and D, and Z has two attributes D and E. We have the number of tuple for each relation. Okay, and we have the number of distinct values for each attribute in each relation. Okay, so we have the number of distinct values for attribute A in relation W, attribute B in relation W, and the same goes for the rest of relations along with their attributes. Okay, so he asks us to use these statistics to compute or estimate the size of the following 9 relations. Some of them are pretty easy, pretty straightforward, and some of them are a little bit tricky. Okay, so read the question twice. Okay, review these statistics, try to find the common column between each pair of relations, and pay much attention to each one of these 9 relations. Okay, so let's solve them one by one together. Okay, the first one, join the 4 relations. Okay, we can solve it by computing the size of joining W and X, then join them with Y, then join them with Z. However, there is a shorthand formula. Okay, the shorthand formula is the following: multiply the number of tuples for each relation, all of them by together in the numerator like this, and divide this numerator by the maximum of distinct values for each attribute that we use to join each pair of these 4 relations. So the maximum for attribute B in both W and X times the maximum for attribute C in both X and Y times the maximum for attribute D, maximum number of distinct values, okay, don't forget that, in both relation Y and Z. Okay, and you can prove this shorthand formula easily from question number 2. Okay, here we multiply T of R by T of S over the maximum number of distinct values for attribute B in both relation R and S, which got us 40,000. Okay, then we multiply these 40,000 by T of U over the maximum of number of distinct values for attribute C in both relations. Okay, this relation and relation U. So we can form the shorthand formula by multiplying these 2 fractions together. Okay, so T of R times T of S times T of U over the maximum number of distinct values for joining both relation R and S times the number of distinct values for joining these 2 relations with U. Okay, based on column C. So this is the answer of the first question. The second one and third one, they are pretty the same. Okay, number 2 and 3, they are the same, and they are very straightforward. Select A equal 10 for relation W. Okay, so T of W over VW A. Okay, T of W equal 100 over W VW A. 100 over 20 gets us 5 tuples. Okay, correct. Number 3, T of Y over VY C. Okay, this is select equal. Okay, T of Y equals 300 over VYC. 300 over 50, it gets us 6 tuples. Correct. Number 4, we want to join the with the left side of this statement. Okay, the left side of this statement is select from table Y where C equal 20. So table Y and Z, let's look at table Y and Z. They have a common column, right? Which is D, right? D. Okay, so we can join them. However, before join Z and Y, we will filter Y using this select equal condition. Okay, so let's filter the total number of tuples in Y using this select equal. So T of Y, this gets us the following: T of Y over, yes, just like number 3, VYC 6. So we will join these 6 tuples with Z. Okay, so let's write it down. New discard. Okay, so this will not join all of the tuples in Y with all tuples in Z. This will join the resultant tuples from the left side of the join statement with all tuples in Z. Okay, nice. So this select equals T of Y, or gets us the following number of tuples over V Y C. Okay, yeah, that's why I love Linux. Okay, I can scroll the background. Okay, 300 over 50 gets us 6 tuples. So we will join these 6 tuples with all tuples of Z. Okay, so let's apply the rule. Yeah, six times T of Z 400. Okay, over what? The maximum of what is the common column between of Y and Z in both of them? D. Okay, so the maximum of VYD and VZD, the maximum between 50 and 40 is 50. Great. Okay, let's simplify this without using the calculator. 400 over 50, 8, 6 times 8 equals 6 times 6 equals 36, 6 times 7 equals 42, 6 times 8 equals 48. Okay, let's check our answer. Yeah, 48. Excellent. Number 5. This is a simple cross product. Okay, T of W times T of Y. Okay, T of W equals 100 times T of Y, 300. 3 and 4 zeros. This cross product gets us 30,000 tuples. Yes, just like this. Okay, back again. Number 6. Okay, select all of the tuples from table Z such that D greater than 10. So T of Z, this equals T of Z over 2 or over 3. Okay, so let's check our answer. Yes, T of Z for 100 tuples over 3 gets us 133 tuples. Okay, number 7. This is an AND operation. Okay, so however you must pay much attention because this is a little bit tricky. Okay, we can compute the number of tuples that satisfy the left side condition. However, the right side is not greater than or less than, it's equal. Okay, it's another equal. So let's do it step by step. New discard. Okay, W. Okay, we are working on table W. So the left side of condition, the formula for computing the number of tuples that satisfies the left side of the condition is T of W over VWA. Okay, 100 over 20 gets us 5 tuples, only 5 tuples. Okay, okay, how many of these 5 tuples that also satisfies the second condition? Okay, so apply the same equation, however instead of T of W we will replace it with 5. So 5 over VWB. Okay, 60, 5 over 60. This one, 100 over 20 times 1 over 60. Okay, okay. So 100 over 20 times 60, 0.08, nearly zero number of tuples. Okay. The one after it is pretty simple. 5 times 1 over 3, okay, or 1 over 2 for relation W. Okay, let's check it. T of W over VWA equals 100 over 20 times 1 over 3. Okay, this gives us 2. Okay, nice. The last one asks us to compute the number of tuples that results from joining x and y. However, the join condition is x dot c less than y dot c. So here the common column between x and y that we will use to join x and y is column or attribute C. X and y, yeah, the common column is C. Okay, so we can think of it as a cross product to compute all possible pairs of tuples for both relations x and y. Then we need to select using this condition less than. Okay, we need to select from relation R, relation Y. Okay, so X join, okay, and X dot C less than Y dot C, join it with Y. So let's compute the cross product of X and Y to get all of the possible pairs combined together for both relation X and Y. Okay, so T of X times T of Y. Then from these, let's select the tuples that satisfy the following condition. So X, select X dot C less than Y dot C. Okay, sorry, Control Z. From T of X times T of Y. And the number of tuples, the formula for this type of SQL queries is T of X times T of Y, or the number of tuples of the relation. So we can consider this as a relation, over 3. D of x times d of y over 3. Okay, we are finished with the first 3 questions. Let's proceed and solve question number 4. Consider the following schema. Okay, fruit juice table or relation fruit juice, which has the following attributes: brand, name, type, sugar. Okay, factory, and it has the following attributes or columns: brand, city, revenue. And look, I think this is an abbreviation for the word location. Okay, table location, which has city and state attributes. Fruit juice.brand is a foreign key to attribute factory.brand, and factory.city is a foreign key to attribute location.city. Okay, so these tables reference each other through foreign key reference the attributes of each other. Okay, so fruit juice.brand, okay, is a foreign key for factory.brand, and factory.city is a foreign key for location.city. Okay, and he gives us the following statistics: the number of tubles for fruit juice, factory, location, and the number of distinct values for each of the attributes in each of these 3 tables. Okay, brand, name, type, sugar, brand, city, revenue, city, state. Okay, so he is asking us to estimate the number of result tuples for the queries, the following queries: select from fruit juice where type equal mango. Okay, type. Okay, so this is select over from fruit juice using the attribute type. So the rule is simple: T of fruit juice, the number of tubes in fruit juice, over the number of distinct values, okay, in table fruit juice for attribute type. So 10,000 over 10. So this query gets us 1,000 tools. Okay, select where a revenue greater than 20 million. Okay, select from factory. Okay, and the values of attribute revenues are between 300 and 4.5 billion. Okay, inclusive. So in other words, he gives us the minimum and the maximum. So I will not, in this case, in case he gives you the minimum and maximum values, we will use the rule of minimum and maximum value, and this is greater than. So the rule is, let's remember the rule. Okay, the rule is maximum minus value over maximum minus minimum plus 1. So the maximum is 4.5 billion and the minimum is 20 million. Sorry, the value is 20 million. Okay, so 4.5 billion minus 20 million over 4.5 billion minus the minimum 300,000 plus 1. This gets us 0.99. Okay. So after computing f using the maximum and minimum values, let's multiply it by the number of tuples in table factory or relation factory to give us the number of tuples that satisfies the following condition. Okay, the last one is to join fruit juice and factory and city. Okay, to join the three tables together. So let's multiply the number of tuples in fruit juice by the number of tuples in factory, and by the number of tuples of table location or relation location over the maximum number of distinct values for each pair of these three tables. So let's first join in the I'm talking about the denominator. Let's first join fruit juice and factory, get the maximum value of the distinct values for these two tables, then join factory with location, and then join factory with brand. Okay. Okay, the last question in this practice assignment is about proposing different logical algebra trees. Okay, so suppose we want to find the list of factories making banana type in Cairo. Okay, this is an extension for the previous problem. Okay, the result set should contain unique tuples, so we have to filter out the duplicates, and then he lists these three linear algebra equivalence rules to use it to propose two different logical algebra trees. So we have three tables: fruit juice, factory, and location. We want to select all of the tuples that makes banana in Cairo. So the location is Cairo, city equals Cairo, and type fruit juice type is banana, and factory dot city is Cairo. So the first and the simplest solution is to join the three tables, fruit juice, factory, location, with the following two conditions: type equal banana and city equal Cairo. Okay, so this is the basic idea or the basic linear algebra tree to execute the following requirement. Okay, and using this rule right here, we can propose another solution. Okay, we can propose another solution by applying the two conditions separately on each relation and join the result of each site or of each part. Okay, so this is the tree for the first solution: join location and factory, then join fruit juice, then filter the result set using these two conditions, and perform the last step is to perform distinct, because he instructed us to filter out duplicates. Okay, and the second solution is to filter out fruit juice and filter out factory, and join the result set of each select statement with location all together, and perform distinct. Okay, so here's the tree. We will join location with factory tuples with city equal Cairo, and fruit juice tuples with type equal banana, and perform the distinct operator. Okay, this is the end of tutorial 7. I hope you'll enjoy it, and don't forget that you have to watch the lectures, because we don't cover all of the concepts in each lecture during the tutorials, so you have to watch the online lectures and study well. Okay, so stay safe, take all the precautions to avoid the infections. Okay, and I wish you good luck. Thank you so much. Goodbye.